Welcome to Cook the Science. I'm Thomas Michaels. I'm a professor of soft and living matter physics here at ETH in the Department of Biology, where I'm also part of the consortium bringing materials to life. And it's really amazing to see so many of you. I think coffee resonates with everyone. So we have really a full booked house. And this is the first Cook the Science lecture of this 2025. And this spring series is promising to be a really nice one in terms of various topics that we are going to cover. And so with Cook the Science, very briefly, what we want to achieve is we want to bring science closer to the public, to you, to demonstrate how science is something that is not distant, complicated and far, but it's something that we all have in our kitchens and we can play with. And so cooking is really the best way or a very good way to achieve this because we catch people really in their daily life. And every night we have different kitchen science topics, which we try to break down from the point of view of the science and also with the help of chefs that do live demonstrations. And the topic tonight is, as I said, coffee. And who doesn't need coffee? So I would actually like to start with a quote from a famous mathematician, Alfred Renier, who says that a mathematician is a device for turning coffee into theorems. So I have to remind you, we are actually in the mathematics department. Here I had my analysis one lectures as a student. So I think this is, I very much relate to this sentence over here. And to illustrate this topic of coffee, tonight we have really a special guest, Shem Leupin, who is from Stoll Cafe. So many of you from Zurich, you probably know Stoll Cafe because it's sold and it's used in many different coffee shops. Shem is also a very important person in the coffee scene. He has been a Swiss Barista champion and is co-owner of a specialty coffee here in Zurich called Coffee. I guess it's a very, very appropriate name, I would say. So we are very lucky to have you here tonight to share your secrets as a barista. And so we have really a lot to cover tonight. So let's start diving into coffee, and the floor is yours, Shem.
Yes, thank you. A pleasure to be here. All right. So we start off the round with the origin of coffee, which you could actually break up into two different categories. Firstly, of course, the geography or the botanics, or the first consumption of coffee. And for a quick quiz question and an easy prize of a bag of coffee, can anyone name where the origin or the beginning of coffee was? Yes, correct. You can. That was an easy bag of coffee. All right. So we have the beginning of coffee in the story of coffee in Ethiopia. Here is also where Arabica originates from, and the other coffee that we all have heard of is Robusta, which spreads across Central Africa and the Western Sahara, Sub-Sahara. These were then spread to the European colonies, and which now become the coffee belts. These, of course, the fertile or the ideal growing areas for coffee. Now, if we look at the plant, the coffea, the genus, there are over 120 different species within the genus. And of those 120, we have 5 that we drink. And of the 5, we have Arabica and Canephora or Robusta being the 2 main coffees we consume, of which Arabica is 65% of world production, roughly, and Canephora or Robusta are around 35%. As you see, they look quite similar, but there's some differences. We have difference in size and shape. So Canephora is more round and smaller, and Arabica is slightly oval, longer shape with a wavy center cut in comparison to the straight center cut of the Canephora. The two coffees have quite distinct profiles in the cup, which the Arabica, and the reason why most of a lot of the discussion is around Arabica, is because of the two. It has floral, sweet, chocolatey, fruity, acidic, and is quite complex. Canephora or Robusta, in comparison, is quite earthy, bitter, intense, woody, and can be quite harsh. Though, important to mention, Canephora has more caffeine, so if anyone is purely in it for the hit, then I would go for Robusta. Now, if we move away from just the genuses or the plants themselves and we get into processing, the processing has a very big influence on the way the cup tastes in the end, and it's broken up into 3 general categories. But before we get into it, we just have a quick look at the coffee cherry, a cross-section. And here we can see a mucilage or a honey-like sticky coating around the seed of the cherry. And on the outside, this here, the skin is quite leathery, quite tough if you chew on it. It's sweet, but it's not something you would eat. And then in the middle, you can see the bean, or what we then consume as coffee. So in the first process, we have washed. The coffee is harvested, and directly after the harvest, the coffee will be pulped and then removed from the fruits. It goes then into fermentation tanks where the mucilage or the sugars are removed, and then the coffee is washed. Any defects here will be through floating removed, and then the coffee is dried. If we go to the other extreme, we have natural. So here, the coffee is dried full fruit, so in the cherry, and then will be dried either on raised beds, as is common in Africa, or on cement patios, as you will see a lot, or as one sees a lot in Brazil, where the production, of course, is a lot larger and requires larger surfaces. In the end, we have this dry raisin-like looking fruit left over. This will be broken out of the shell, and in the end, the coffee looks much similar to the other processed coffees. The one in between is honey. So here, the coffee is pulped, the mucilage on the outside remains, and the coffee will be dried with the mucilage on. This gives you a cup profile that sits somewhere between the natural and the washed profile. So the washed profile, you have a very clean, crisp cup. It has quite high acidity. It's quite tame in the aroma department in comparison to the natural, where you have strong fruity aromas, more body, quite chocolatey, and if you push the fermentation or the processing, you can get some quite funky, almost like rum notes coming through into the coffee. And with honey, depending on the processing, you sit somewhere in between those two extremes. But if you look at the cups on the table in front of you, we have 2 different coffees from 2 different origins. They're actually processed the same. They're both natural coffees. One is a Brazil and the other one is a Rwandan coffee. If you stir with your finger around inside the cup, you'll smell a bit.
What a lovely sound.
It's very good. So I think you can smell you can smell the difference between the two. So one is very grainy, grassy. The other one has a slightly fermenty, or you can smell there's something more complex going on. That gives you a good indication of the different qualities that you can have in coffee. Even already now you see in the green coffee stage, so not yet roasted. But if we were to grind this, it wouldn't be very soluble. It would taste quite grassy, much the same as it does now, be very watery, and the whole exercise with the caffeine would be quite useless. So we need to roast the coffee. We need to, in the roasting process, we begin with the endothermic reaction where we're actually absorbing heat as the coffee is drying. And we go through this process, and as the coffee loses its moisture, the carbohydrates and the sugars will begin to react, and we get into the Maillard reaction, and we change into the exothermic reaction where the coffee begins to give off heat. So as we progress into the roast, we're actually reducing heat, but the temperature of the coffee is actually rising. But we still can't drink it yet. The first important marker in the roast is the first crack. So the first crack is a loud cracking sound you hear inside the roasting machine, and not ready to take it out yet, but you know you're pretty close to the first drop you can make, and that is the light roast filter coffee. So here we have a roast that is free of roast aromas. It's maximising the complexity of the coffee. So we're using it for a very long brew ratio, so a lot of water to coffee, and it's going to be quite acidic, very fruity. If you like it, I like it. It's very good. But for espresso, we need to go a bit further, or we generally like to go a bit further. It gives the coffee a little more time to develop. It expands a little more, becomes a little easier to extract. So it gives you coffee at a much shorter brew ratio. It's easier to achieve a balanced result in your cup. Then as we move along, we move into the medium roast area. This is sort of, one could say, tries to have a bit of both worlds. So we have the terroir still in the cup, but we're moving into roast aromas. And the further we go along, we get to dark roast, or what we predominantly drink. Here, we're drinking pretty much roast aroma, and the terroir, the character of the coffee, is pushed back far into the background of the coffee. Then we get to second crack. Here, the oils are now pushing to the surface of the coffee. I personally wouldn't do it. If a coffee looks like this, it's susceptible to oxidization and will become rancid. If you like that taste, that's what you're looking for. The further we go along, we, of course, sooner or later end up with the fire brigade. I wouldn't push it that far. I would hope we've stopped before. But it's a good-looking, shiny coffee bean. So the coffee, what happens in the process, the cell walls expand, and then the new compounds that are formed during the roasting process are hidden in these areas, and when we use the water, we're looking to get around 18 to 22% is our target of wanted solubles, and there are about a further 10% of solubles that we don't want in the cup. So when we move on to the brewing, before we start brewing anything, the most important thing is that we have good equipment. That doesn't necessarily mean expensive equipment, but it means filtered water, so soft water, because a hard water will have a buffering characteristic, which means your acidities in the coffees will be flattened, muted. It can make the coffee taste harsh. Then scales. As you see, everything that I do, there's a scale for everything on the table. I know it seems a bit extreme. I'd hope at a university using scales or being exact, you understand. It helps us repeat good results, and it also helps us correct mistakes that we make. So if we make a mistake, it's easier to find what we need to correct, and helps us move on to a better result. Then the coffee grinder. A big mistake in making coffee is that we pre-ground coffee. the coffee oxidizes very quickly, the volatile aromas escape, and if you choose the wrong setting when you're at Coop or Migros and you get home and you want to make your coffee and now the grind setting is wrong, you are stuck with that grind setting. So if you invest in just a simple hand grinder, you can change your cup of coffee at home quite dramatically.
Perfect. So now I'm afraid we have a little bit of physics. So yes, so let's see how we think a little bit about the brewing of the coffee. And so we always have equations, and you know what to do when an equation comes up, so be ready. So when thinking about brewing coffee, the single most important equation you need to know is Darcy's law. So Darcy's law is a law that has been discovered by Henri Darcy, who was a French engineer in Dijon. So at the time, the city had problems with having clean water. And so they started thinking about developing a filtration station. And so they put Darcy in charge of developing such a station. And so he played a lot with flows of water through beds of sand. So actually, if you want to obtain a very simple way to actually filter water is to flow water through sand. And so by experimenting with this, he actually came up with this law that is called Darcy's law in his honor. And here it is. So what have we got? So the Darcy's law is the law that governs, in the simplest setting, the flow of a fluid through a porous media. So what we have here is imagine you have a bed of a granular material. So granular materials are materials like sand or coffee grinds. So these are your coffee grinds. And imagine that your coffee grinds here have, say, a thickness H, and you have a cross-sectional area A here, so the cylindrical shape. And then the question is how easily or how much water is going to percolate through this bed of coffee. And so the law that governs this is Darcy's law. And so what we have here is Q, which is the flow rate. So it's the volume of liquid that flows per unit time through this bed here. And so what are the different terms in this equation? So there are two driving forces that drive flow in this equation. So one driving force is a pressure gradient. So that's actually the difference of pressure across the distance h here. And this comes with a minus sign because flow goes from high pressure to low pressure. So if you want, the pressure gradient is negative. And another driving force that can cause a fluid to flow is gravity, of course. And so you can already see where we are going with maybe filter coffee or espresso. And we have also other parameters here that define the resistance of this flow. And so on the one side, the flow is inversely proportional to the viscosity of the fluid, which makes sense. A more viscous fluid will flow slower. And also we have, very importantly, this parameter K here, which is called the permeability. And so what is this permeability? So if you look at the units of this permeability, it has units of meters squared. So it has units of an area. And whenever in physics a quantity has a units of something, say, for example, an area, it's never by chance, because it has a meaning. And so we have to ask which area. Okay, so we are talking about flow through porous media, and so, of course, the pores. So we are talking about the area of the pores, and the pores are these tiny channels that the water finds to go through this bed of coffee grinds. And so there are two key parameters that determine the permeability. So one is the pore area, so the size of these channels here that are formed by the water. And this is something that we can control as a barista by tuning the grind size. And this is why Shem was saying it's really important that we get our grind size right, because that will really determine how much flow we will get through our bed of coffee. And the other quantity that determines the K is the porosity, which is the fraction, the percentage of the basket that is not containing grinds. So if you want, is the free space. So it's a fraction of volume that is free, available for the water to percolate through. And this is something that we can control, for example, by compacting our pressing on our coffee grinds, which we do, for example, when we do the tamping with the espresso. So in this manner, we are actually decreasing the permeability, increasing the resistance of the flow. And what you can see here is actually a simulation of a flow through a porous media. So here you see with a red color means large flow, and you see here these white particles here. You can imagine them as the coffee grinds, and what you can see really is how the water flows through, percolates through here, and finds these kind of channels, which are our pores that control the process. And so this is the basic physics. So this equation has really more or less all we want to describe tonight, because on the one side, when we focus on the gravity term here, we have a description for filter coffee. And when we focus on the pressure term here, we go more into preparations like a mocha pot and the espresso. And so tonight we will actually go through these different preparations with Shem, and he will reveal all his secrets about this. And so let's start with the simplest, I guess, at least from a physical perspective, from an equation. So filter coffee.
All right. So I just make sure the kettle's running. Yep. So the filter coffee was actually invented at the turn of the last century by Melita Benz, who was quite obviously sick of a muddy cup of coffee with coffee grounds in it, and experimented with different papers and found out that blotted paper from her son's exercise book was the best paper, which also, I suppose, the next day was the worst excuse for not handing in homework. So the filter coffee is actually pretty unchanged, or hasn't gone through many changes, and is quite still quite simple.
Yes, not the equation though.
No.
Very nice. So let's go a little bit through the physics of filter coffee. So as I said, so filter coffee is a flow driven by gravity. So if we go back to our Darcy's law and we focus only on the gravity term, then our equation for the flow rate, so amount of volume of water that flows to our coffee bed, is simplifies to this expression here. And what you realize here, actually, even if you don't understand anything about these Greek letters over here, what you see is there are a lot of them. So that means that there are a lot of parameters that we can tune. And this is what makes, I think, making coffee so difficult, because you have so many variables that you can change and tune and play. And that really makes the phase space of possibilities explode. And so we have to somehow deal with this. And so what we can do is we can reduce the dimensionality a little bit, and we can fix some of these parameters in our recipe, and then leave just a subset of these parameters, of these variables, for us to tune, to optimize, to get the optimal result. And so what I mean with this is I'm going to introduce a few concepts from the barista world. So Shem, please tell me if I'm wrong. So effectively what you do is you fix a recipe. And so with fixing a recipe, it means we define what we call the brew ratio, which is the ratio between the dose, the coffee dose, so in grams, so how much coffee we actually put in our filter, for example, in our portafilter, in the espresso machine, so that I'm going to call it D, and the beverage mass in grams, so how much beverage we are going to obtain at the end. And so this ratio between D and W is called the brew ratio. And so we define this for different recipes. Different recipes require different brew ratios to obtain the right profiles, the right extractions. And then we also fix the brewing time. So our goal is to achieve that recipe in the right brewing time. And so from the brewing time, we can estimate by dividing the beverage mass with the delta T, so the brewing time, the flow rate. And so you can see from this equation here that if we define the flow rate, we have the other parameters here fixed, then we can determine K, which is our permeability. So remember that depends on the coffee grind size, etc. And so that means that we can now play with the kappa, with the grind size, and tune the grind size in such a way that we achieve the right recipe in the right brewing time. And so if you take too long to achieve this brew ratio, that means you have that your grinds are too fine, so you have to grind a little bit coarser. And if you take too little time to achieve the recipe, it means you've gone too coarse, and so you have to make your grind size a little bit finer. So this is really a little bit how we can think about brewing coffee, also from the perspective of linking these different variables. And now I think Shem is going to reveal his recipe for filter coffee. So here are the parameters.
Yes, thank you. So today, by the way, everyone should have a cup of coffee in front of them by now, I think. No? Patience brings coffee. There will be coffee coming. There shall be coffee in a moment. Those who have coffee in front of them, please start drinking. It was quite a task to get this volume of coffee for this many people. So there was a time between the brew and serving. So I think the quicker we drink it, the better. And I would say enjoy, and I'll explain. It's the coffee I'll be brewing here on stage as well. I'll explain more to that in a second. So the brew ratio we're using here today is 1 to 17. So 1 gram of coffee to 17 grams or roughly 17 grams of water. I make it slightly simpler. I'm doing 6 grams to 100 grams of water, which makes my recipe a little easier, and I don't need to use the calculator. And then I use a temperature of 96 degrees. You can changing the temperature of your water can change the extraction or how well you extract. So the lighter the roast, I'm using a very light roast here. The lighter the roast, the higher I'm going to use the temperature. And if I use a very dark roasted coffee, I don't want to it's going to extract very easily, so over-extract very quickly. So I'm going to drop the temperature, and if I go really low, I'm going into mid to high 80s with the temperature.
If I may say from the physics, so if you remember Darcy's law, we had one term, the viscosity there of the fluid. So actually the viscosity goes down very much with temperature. So water at high temperature is way less viscous than water at room temperature. And so that actually makes it flow much easier to our coffee bed. So that's really one aspect where the temperature plays a big role in our equation.
For this recipe, I will have an end time of around 2 minutes 30. I'm hoping that I'll hit that. And the grind size is around table salt. Of course, I can't tell you the exact grind size, and there is no universal setting. But as Thomas mentioned before, it is the components of the recipe which then end up with your grind size. So that's how you would calculate your grind size. Of course, that's a bit of trial and error in the beginning, but the more you do it, the quicker you get. And I suppose, and most coffees, if you stay within a certain roast degree, light, medium, dark, your grind setting generally tends to be quite similar. So we're going to start by grinding the coffee. Just for the sake of speed, I'm using an electric grinder. You can do it at home with the hand grinder. I weighed off before. I did use a scale, 18 grams. So that you can all see, it's a bit far out for me, but we shall manage. We're just going to wet the paper filter. Because the paper is actually bleached. It's not so much the taste of the paper that I'm trying to remove than the heating up the glass or the porcelain, depending on the filter you're using. So we warm that up. $18 grams. Just level the bed. Then we start with a bloom. That means 2 to 3 grams of water per gram of coffee. This is just enough for the coffee grounds to swell, release or off-gas the CO2, which you can see here bubbling. The fresher the coffee is, the more CO2 it's going to have, so the more intensely it's going to bubble. If I give it more water, the coffee is just going to flow to the top and the water will bypass below. Now, going again, second pour. We're looking at a pour of about 8 grams per second, and we're trying to have the stream just before it breaks up. I'm trying not to hit the walls. One circle to make sure any floating pieces. Maybe a quick stir if you see coffee sitting up high on the walls, and now we let the coffee or gravity do its work. So now, as Thomas was mentioning, the easiest way, of course our sensory skills when we start with coffee aren't that refined yet, we will stick just to the 2 minutes 30, but after a while we'll notice if we have a coffee that's tasting quite hollow, sour, not very complex, we're going to go slightly finer to try and extract more. And if we have a coffee that's tasting bitter, not to be confused with sour, we are going to go slightly coarser in order to get rid of this bitterness which comes from the over-extraction. So the coffee you're now drinking, as you'll notice, is quite tea-like. It's very fine. It's not what we would classically associate with this, the American diner style filter coffee we saw in the movies. It's very light, almost like a fruity tea, quite complex. This is a special process coffee from Colombia, and here we have an extraction around 1.2% TDS. So we have over 98% water in this brew.
So just to explain, TDS is total dissolved solid?
Yes.
Yes.
A term we use a lot in brewing coffee.
Yes, that's so you can all claim you are now coffee nerds.
Now, I didn't say it stopped, but I'm guessing it was on point.
Yes. Very good.
All right, then we move on to the mocha pot. Something that in the barista world we don't talk about too much.
It's interesting from a physics perspective, so that's why I put it in.
Yes.
So, thank you.
We don't talk about it very much, but the interesting thing is everyone has one at home and everyone uses it and everyone makes a ton of mistakes when they're using it. So I'm hoping we can help that. So the mocha pot began its story in the 1800s, and it wasn't until what didn't become a household object until Alfonso Bialetti patented the mocha pot, or the Bialetti as we know it today, and it didn't actually, if we want to keep in terminology, pick up in steam until the 1950s, when it then became a household object. So Interestingly, although we like, or a lot of people call it an espresso maker, or it's associated very much with espresso, we're actually much closer to filter coffee than we are to espresso. So we have a brew ratio of 1 to 10, where you'll see later in coffee, where espresso, we hover around 1 to 2. And we have a much lower TDS, so a much lower total dissolved solids in the end drink. Here, we use the ratio of 1 to 10 we measure by filling to the pressure valve inside the bottom part of the mocha pot. This will give us the 10, and then from that we calculate how many parts coffee. Overfilling it will create a higher pressure. Higher pressure as we'll see later on, also creates more heat, and then we're very quickly creating an over-extraction. I find we get a cleaner cup, and if we take it even slightly more extreme, we can just take the AeroPress filter, and by placing it in the bottom here, we get an even cleaner cup, if you like the cup slightly cleaner or clearer. We're using a medium to high heat. I would use boiled water, water just off the boil. That way, the heating process, the coffee isn't actually sitting in the water vapor, so it's not actually extracting through the heating process. So we're going pretty quickly straight into brewing. And unfortunately, what makes the Bialetti quite tricky is we don't have a brewing time, because we can't see when water comes in contact with coffee, because it's a closed process. Here, we very much have to rely on our sensory skills. So depending on how we like it, if it's tasting thin and acidic, watery, then we know we need to go finer. If it's tasting bitter, too strong, intense, we know we need to go more coarse. Just one before I forget, when we see the coffee exiting the top of the spout here, that's when we turn the heat down to low and let the coffee run out. And if it starts to sputter, I usually put it into cold water to stop the extraction, to avoid any over-extraction. I think that's, and don't press it down. That's, before I forget. That's a quick run through the Bialetti extraction.
Yes, exactly. Don't press it down. And we now try to understand why is it? So what's the physics behind it? But I would like to start off with a video first. So what you see here is actually a neutron video made with neutrons of a mocha pot. So that because it's made of aluminum, so actually the metal is transparent to the neutrons and the water is black. And so that actually allows you to see through the mocha pot. But of course, that's not for every day. I mean, it costed a lot of money to make this video, so we better enjoy it. So what do we have here? So we have actually at the bottom here, that's the boiler. So that's where the water is. So we heat the water up. The water then boils, creates a steam. Then the steam here pushes the liquid up and then goes through the filter. That's where the coffee grinds are. And then is pushed up to the top. And that is where then the coffee is collected. So that's really the basic principle of the mocha pot. So if we go back to our equation of today, I guess by now, I mean, at the end, I should do an exam. So you should all know this Darcy's law. So if we go back, now we are talking about pressure. So really what drives this process is the pressure from the steam. Okay, so we have really here boiling water, and then when it reaches 100 degrees, it boils, it creates this steam. But because we are in a closed volume, so volume is fixed, as the steam is created, pressure goes up. And so this pressure then means that effectively the steam is acting as a spring, so it pushes the liquid up through the filter and then up this way. And so what the driving force here is really the elasticity of vapor. And the point is that this elasticity is not for free. Many things in life are not for free. Unfortunately, even the elasticity of vapor is not for free because it comes at the cost of temperature. So higher elasticity means higher temperature, and higher temperature is bad for coffee because you over-extract and you get a bitter coffee at the end. And so the way to think about it is another equation, which is the Clausius-Clapeyron equation. So the people that have done thermodynamics here, you can scream. I never liked it, to be fair. But so what you have here is the phase diagram of water. So what a phase diagram is tells you the different phases, states in which water is as a function of the temperature and the pressure. And so you see it can be in a solid state, as a liquid, or as a gas or vapor. And so, for example, here on this point here, you know that 100 degrees is the boiling point of water at 1 bar, which is the pretty much atmospheric pressure. And so now what happens with the mocha pot? As I said, we have here the boiling water, which creates the steam. So we have coexistence of liquid and its vapor. And so that means that we have to move, we are constrained to move along this line here of coexistence between liquid and the vapor. And this is exactly what this equation tells you, that is, as you move along this line, as you increase pressure, you are increasing temperature as well. And of course, in order to filter, to have the water go through the bed, you need a pressure gradient. So your pressure has to be at least more than atmospheric pressure. But the more pressure you put, the higher the temperature will be. And so that is really the price you have to pay. And so the optimal conditions for doing mocha is to have a pressure of about 1.4 bars. So that's about 0.4 bars of excess pressure from the atmospheric pressure. And because this gives you a temperature at the end of the extraction of about 110, 115 degrees. You don't want to go higher than this temperature over here. And so you see really that you need pressure to go through the filter, but you are paying the price of higher temperature. And this is why you don't want to have too much coffee in your mocha pot. You don't want to grind it too fine. And you also don't want to press it down, because all of these things are going to increase the resistivity, the resistance to the flow. So they are going to reduce the permeability K here. And so which would mean that you would need a higher pressure gradient in order to achieve the same flow rate. And so that means that you would need to go to a higher pressure to extract, and that means higher temperature, and your coffee is bad. Okay, so that's really fundamentally the reason why we don't want to press down in the mocha pot. But the point is, who told you that this is the best way to make coffee, right? As I said, the reason why we put this in is because it's interesting from a physics perspective. But of course, people realized already initially that, perhaps this is not the best way to make coffee. And actually, in Milano, people have invented the espresso machine. And the espresso machine has one very important characteristic that makes it great. And it's the fact that it has a thermostat and a compressor. And that means that we can now tune the temperature and the pressure independently. So we are no longer stuck to being along this line here, but we can move everywhere. We can just go everywhere. And that means now we have a whole world to explore. We can ask, where is espresso? Where is it? And so what they did at the time is they invited a bunch of sommeliers, and they explored phase space, they changed all the parameters, and then they find out that actually the best conditions for espresso is here. So it's to have a pressure of about 9 bars and a temperature of about 90, 95 degrees. So that actually puts the espresso all the way up here in this phase diagram over here. And now, the fact that we are now extracting at such a high pressure, so we have 8 bars of pressure difference from atmospheric pressure, creates really a completely different drink compared to what you get from the filter coffee or what you get from the mocha pot. And this is why the mocha pot, it's not going to give you an espresso because you don't have the same amount of pressure. And so what are the characteristics or some of the characteristics of espresso that come from this high pressure? There are two characteristics we all like, or at least I do. So one is the crema, the characteristic crema of the espresso, and the other one is also the viscosity of the drink. So the espresso is really much more viscous, a bit luscious, if I may say. So let's try to understand why is it. So it's because of this high pressure. And so that allows us to extract a whole different set of compounds under this pressure, high pressure. And so let's focus first on the crema. So what is the crema of espresso? So the crema of espresso is a foam. And in the context of soft matter, the foam is effectively bubbles of air that are suspended in a liquid, and they are stabilized by so-called surfactants. So it looks a little bit like here. So here it's actually an image of a magnification of the coffee crema. You see all of these bubbles, and this is like 1 millimeter to give you the scale of how small these bubbles are. And if I were to kind of draw a molecular cartoon, it would look something like this. So you have these air pockets, these air bubbles, and the air is actually CO2, which comes from the beans, as we have heard before. And we have this water layer here, which is then stabilized by these surfactants. So surfactants are surface active agents. They are molecules that have two parts. So they have a head, which is hydrophilic, which means it likes water, and they have a tail, which is hydrophobic, which means it hates water. And so what this means is that whenever you have an interface between, say, liquid, so between water and oil, or between water and air, then these molecules will go at that interface. Why? Because they are happy there. Because there they can stick their head, which likes the water, in the water. They can stick their tail away from the water into the air, and they are happy. And by doing that, they create a physical barrier that prevents these bubbles from coalescing with each other. And in that manner, they stabilize the foam. And as I said, these bubbles here are made from CO2, and the CO2 comes from the coffee beans, from really the roasting process. And so how is the crema formed? So why we need this pressure? Well, because at high pressure, CO2 is much more soluble. And so that means that under these 9 bars of pressure at which we are extracting the espresso, we are also extracting CO2. But then as the coffee lands in the coffee cup, now we are back to atmospheric pressure, the solubility of CO2 goes down, and so the CO2 comes out as bubbles, and then which are then getting contained in this foam structure over here. So you really see how it's very important to have this pressure gradient. And of course, it's also very important to have CO2. And this is why it's very important to use fresh beans, or beans that are actually roasted at the right time. I have to admit, when I heard that, I thought, okay, this is one of these nerdy things that is made for you to buy more coffee, really, from, you know. But actually, I got like one of these fancy coffee machines at home, not as fancy as this one. And we played and we tried to make this coffee, and this crema never came out. And we played with the grind size, and why is that? And then we got fresh coffee directly from the coffee shop. We did it, and we got this amazing crema. So really, the freshness of the beans is very important, because you need this CO2 to make the bubbles. And over time, these coffee beans decay, so they release this CO2. And also in the grinding process, we lose a lot of CO2, which is also why you want to use freshly ground coffee immediately after it comes out from the grinder, as opposed to leaving it there for a long time. Now, the other characteristic of espresso that makes it really interesting, as I said, is the viscosity. And here the viscosity comes from the fact that we are also extracting oils in this process, and that creates an emulsion. So an emulsion is when you have tiny oil particles that are dispersed in a continuum phase, so in water. Okay, so think about a salad sauce, for example. So it's something like that. And so it's really this emulsion that gives you the viscosity. And you probably know when you make a salad sauce, you mix vinegar and oil, that you actually, because you are making this emulsion, you are actually creating a sauce which is much more viscous. And this is why we like it. And in fact, there is another equation that explains this phenomenon, why emulsions are more viscous, and so in general. And so this is the Taylor equation, which is describes the viscosity of a dilute emulsion. So when you have, let's say, a small amount of oil in water, and as a function of the phi, which is the volume fraction of the dispersed phase. So this is the volume fraction of oil that you have in your emulsion. So the more you have, the higher it's going to be your viscosity. And eta c is the viscosity of the continuous phase, so in this case water. And lambda, the parameter here, is the ratio of the viscosity of the dispersed phase, so the oil over the viscosity of the continuous phase, which is the water. And so now let's go to making some espresso, I guess.
Yes. All right. Just before we move on to espresso, something that I forgot actually in preparing, and because Thomas now spoke about it. The freshness of the coffee, which you haven't spoken about before, is not directly from the roasting machine. Then we have a high amount of CO2, too high actually. We're looking at around 2 to 3 weeks, depending on the coffee. And you will notice if you use a very fresh coffee, I watch people at the roastery always picking the freshest roast date to take home to get lots of crema. This crema is quite unstable, creates a lot of bubbles, creates high crema. This crashes very quickly and doesn't look very good, and also has quite a harsh taste in the cup. So around 2 to 3 weeks is what I would wait, and this can apply also to filter coffee. All right. So just a little history again. Again, in the 1800s, much similar story to the mocha pot. We're using steam pressure. And then it was in the the beginning of the 20th century, Moriondo and Becerra invented the coffee machine, and was then, the patent was sold to Pavoni. And in 1961, there was a large development again when the Faema E61 was built and the electromagnetic pump was born. And this sort of is what the modern, or the beginning of the modern espresso machine. What we've been talking about, the viscosity, that's a very important part of espresso, and depending on how we like it, as one element, or there are a few other elements that come into play as well. We also have roast intensity. So if we're using a light roast or a dark roast, this will also sort of give us boundaries as to how extreme we can go. The lighter we go, the longer or the more water we're going to want to use. So a higher brew ratio, because we need more water for balance, and also for extraction, to extract more coffee, because the light roast isn't quite as extractable or as easily extracted as a dark roasted coffee. So a dark roast coffee is going to allow us to make a ristretto, which is very short coffee, which we enjoy. You see a lot in Italy, very short.
A bit too short, I have to admit.
Yes. So if we do this with a light roast, we're going to get this very acidic, intense, overbearing espresso. And if we do take a dark roasted coffee and make something longer, we're generally going to run into over-extraction a little easier. But generally speaking, we're in this range here. Now, even though many people call it the espresso, it's fast, but it's not that fast. If if we see here, we're aiming for a window somewhere between 20 to 30 seconds. The more we know about coffee, the more we can play with these variables. But if we go too far down, we are going to be sour, salty, watery, bland. And if we go too far up in the extraction, we're going to over-extract. We have this bitter, dry, intense cup, which is also unpleasant. I've heard a lot in cafes before. The person who doesn't like the long espresso and wants a short espresso, please pull the coffee out for me earlier. Of course, with the grind set for an espresso or the size shot we're using in the cafe, what would happen is we're stopping in this area here. We're actually getting less for our money and not more. So we're losing on the complexity that is actually hidden comes later on in the brew. So it's very important that we aim to go into the full length of the extraction. Now we get into the brewing recipe. So here today I'm using, as you know, as a theme, I'm using a lot of light roasted coffee. The light roasted coffee I'm using, I'm going to do 1 to 2.5. So I'm using an 18 gram basket. So depending on the machine and the size of the basket, I will adjust. Something you must check. You don't want to overfill the basket because as soon as the water hits the coffee, when the coffee swells, it's going to hit the shower head and the coffee is actually going to slow down and block again. And so we have to find out what the volume of the basket is. Generally, I like to use a 93 degrees. It's a good, safe in between. And some machines you can set, some machines you can't, but on this machine I can. And we're looking for 25 seconds. So I'll just go through the motions. If I'm setting the grinder and I'm using or I'm changing something, I want to purge the grinder. That means I'm pushing out the old grounds or an old grind size. This I have to throw away because these were old grounds or old grind size inside here, just to see we're doing everything correctly. So this actually has a scale in it, but just making sure, it's actually just under 18. We want to tap on the side of the basket, not pressing down, because otherwise we create denser areas in the coffee bed. Then we're going to press down on the coffee. The most important thing is that we're pressing down evenly or flat at 90 degrees, and the pressure in itself is not as relevant as how flat or how straight our temping is. We're flushing the group head quickly just to make sure any dirt, any residue from the last coffee is gone. Goes straight onto the scales. Actually, we do too, because we have to make a cappuccino later. And here we go. Now I'm aiming for the 45 grams in 25 seconds. So I'm just letting the coffee machine run. And when I hit the 45 grams, or just before, 44 and a half, and 17 seconds, unfortunately, I didn't hit it. This would now mean that I have to set the grind slightly finer in order to extend the brewing time. And of course, in the other way, if I was to go into above the 25 for my first goal, I would then go slightly coarser.
Perfect. No, we are not done yet, just in case you are wondering.
All right. Now, if you want to go into extremes, from the Barista Hustle website, we have here the coffee compass. So once you start to get used to your extracting coffee and you practicing your sensory, this gives you an idea of the what happens in the cup when we get the brew right, and if we're going into over-extracted or if we're going into under-extracted, which would then lead us into changing either our grind size or the amount of water that we are using for the brew.
Perfect. So let's go into latte art.
Yes.
I guess you are all excited about that.
So far, everything has been quite mathematical, as in the terms of...
Don't worry, it's going to be... There are going to be more equations coming, so...
No, I mean in the sense of how we're doing it at home. We're using scales, we're using a brew ratio. It's very easy to calculate. This, of course, is the hardest thing to learn at home. Of course, practice makes perfect, and I don't know how many cappuccinos you can drink in one day. And sooner or later, I think everyone would probably have become lactose intolerant. But, of course, working in a cafe is the easiest way to practice. So I had a look into, which I didn't know before I got this talk ready with Thomas, but the first mixing of coffee and milk didn't start until the 17th century, which actually tea was just slightly had the edge on coffee. They started just before in China mixing tea and milk. And this then came to Europe, and in Austria, they celebrated this mixing of coffee and milk, and one of the colours of the coffee, or the ratio of milk to coffee, was named after the monk's robe, which was called the Kapuziner, which is where we get the name cappuccino today. There wasn't actually a way to steam milk until the beginning of the 20th century, until Luigi Becerra actually added steam function to his machine. And then a lot later, in 1992, an Italian barista invented the first tulip in coffee, calling it cappuccini decorati, and the discipline of latte art was born. And of course, the mountainous foam was changed. So we
go to the physics now. Sorry.
It's all good.
By the way, it smells so good, and I was actually saying I could get used to this. So, during the lecture, the professor has the barista. Maybe every ETH professor should have this. We should put it forward. Anyway, so let's go to the physics of latte art. I would never believe that I actually prepared a slide on the physics of latte art, and it's actually really interesting. So the way I would like to think about it as a physicist is to think a little bit about what are the variables I can tune, what I can change as a barista. And so the idea of latte art, again, is that you're actually pouring this steamed milk, so you have this milk foam here, and so what can I change in doing so? So one parameter that can actually change is the velocity of pouring. So how fast am I pouring my milk? And this is something I can control, for example, by playing with the height at which I put the jug. And another parameter that is very important that I can actually change is to change the width of the milk jet. So with this, I mean this width here, so the size of this jet here, which is something I can actually tune because of the form of the jug here by playing with the angle at which I tilt. So the more I tilt it, the bigger this L0 is going to become. And so now, the way you can think about this latte art is a little bit as an inverted fountain. And let me explain. So it might sound a bit weird, but so you all know what a fountain is. So you have water that you push up in the air, and then because of gravity, the water falls down. So the more energy you put into the jet, the higher this fountain is going to be. I think that makes a lot of sense. Now, what we are doing here with latte art is we're doing something a little bit inverse, in the sense that we have a denser liquid, which is the coffee, and we are trying to inject into this liquid a lighter liquid, which is less dense, which is the milk foam. Okay? And so, because we are injecting this milk foam, the milk foam is going to go down, but then because of buoyancy, because it's lighter, it's going to be then pushed up, and then it will float. Okay? So you create what you can think as an inverted fountain. Okay? And so, what is really important here is the size of this fountain. Because you can imagine that if the fountain, this inverted fountain, is very shallow, then you're not going to get very much mixing between the foam that you are injecting and the coffee. So you are going to get white foam on the top. But if you have a very shallow, very deep fountain, you're going to get a lot of mixing with the coffee. And so the foam that will come up is going to be brown. And so what you have to do in latte art is somehow to control the parameters, these parameters V0, L0, in such a way that you can actually control the size of this fountain. And so the question is, what determines the size of the fountain? And so here is our next equation. So the size of the fountain is determined by the so-called Fruit number, which is, if you want, it gives you a ratio between the inertial forces, which is the energy that you put into the jet, and the gravitational forces, which are the buoyancy forces that are then pushing the liquid up. And so this Fruit number is determined by the velocity of pouring, V0, by the density of the coffee, rho C, by the density of the injected liquid, so which is the milk foam, rho I, by the gravitational acceleration, and by this parameter L0, which, as I said, is the width of the jet. And so a small Fruit number gives you a shallow fountain, and a large Fruit number gives you a very deep fountain. And so the whole trick of latte art is to play with these parameters such that you create a large Fruit number at the beginning of your pour, such that you are going to get a very deep fountain, mixing, and a brown foam. And then later on in the pour, you want to switch to a lower Fruit number, because that will mean you get white foam. And of course, the barista knows all of this. I mean, knows exactly how to tune the parameters to get the Fruit number right. And when you don't get it, you say, oh, I messed up with my Fruit number. Right?
I'm measuring that every morning, yes.
That's what happens. But yeah, so I actually wanted to demonstrate to Shem that this makes sense. And so we decided to actually make a video. This is Shem doing latte art, and we play it down slowly such that we can actually see and appreciate exactly what happens. And remember, what are the key variables that we are after? On the one side, the velocity of pouring, so that, or the height of the jug, and the width of the jet, so the angle of pouring. And so let's have a look at what happens. So here is the jug that comes slowly. So how is it to see your hand in this?
Better this way than having to do it.
So you see now we are at a very high height. Okay, so the jet is actually quite small, and the angle is not very large. And then we are getting closer, the velocity slows down, and you see how wide the jet becomes. We have changed the angle, we're getting closer, so we are really depositing the foam on top, and we are creating this whiter foam effect over here. Well, I think... Perfect. But of course, we want to do it also live, so no pressure.
No, not at all, not at all. Okay. So my favorite part, doing cappuccinos live.
Yeah, I get a flat white, please.
All right. Yeah, that way is we have to do it again. Okay. So, cold milk. The warmer the milk is, the less time we have to make foam, or if we make a mistake, we can't correct it very quickly. So cold milk is always important. Getting rid of the condensation or the water left in the end of the steam wand to make sure we don't have a watery cappuccino. Then I'm going to put some water into the other jug so I'm not cooling the milk down when I split the milk. Now, the starting position, how well do we see it? Unfortunately, you can't see it very well here. I'm just dipping the tip of the steam wand into the jug, and the most important thing is I'm listening. So I'm looking for this hissing sound, and with my hand I'm measuring the temperature of the milk. My hand can withstand heat of about 55 degrees. Then we go 1, 2, 3. Then we're at around 65 degrees. Roughly, this part is not
that's
very
the difference. So how physicists measures temperature and how barista...
Yes. Of course, the larger the jug, the longer I wait, the smaller the jug, the quicker it goes. Now I'm splitting the milk, because if I poured everything just from the jug straight away, I would have a lot of foam in one cup and very little in the other. Now,
let's give maybe some encouragement.
So I'm swirling the crema just to break the crema up a little bit so there's not these islands of crema. Now I'm going low. And then we have a heart.
Wow.
So it was a bit of a chicken with the heart. Let's see if we do something else. Just getting rid of the large air bubbles. So here we go.
Wow. Wow, amazing. When you do it, it looks so simple.
Yes.
The ones I make are not at that level, but I'm working through my fruit number.
Yes.
Perfect. And I think we are perfectly on time. That's amazing. So thank you very much for coming. I hope you've enjoyed the lecture. You've learned some tricks for making coffee. As Shem said, you don't need necessarily this fancy machine to improve your coffee. You can invest maybe in some small equipment, but very important, like the scale, an ice grinder. And this, I think, with the help of these tricks that we've learned tonight, it's for sure going to improve the type of coffee that you make. And please let us know if actually you do. So we would be very interested to hear about that. And at the end, I would like to advertise the next event that is going to come up in actually 3 weeks on the 8th of April. So as you see from this cubic gelato, we are going to talk about ice cream. So the topic from a science perspective is emulsions and foam. So we touched a little bit about that. So we're going to go deeper into this and how they control the texture and the parameters to make very nice ice cream. And we will have Elif Oskan, who is the founder of Gül restaurant in Zurich, so very famous chef here in Zurich. And at the very end, I would also like to thank everybody, not only Shem, but everybody that has been involved in making this happen. Of course, we are here today because of the work of so many people at different levels, the whole Cook the Science team, all the people that have helped, the student helpers, the camera team. As you have seen, we have also the Swiss television here today. So I didn't tell you because so you would look a bit more natural. So, and also I would like to thank the Department of Biology, the Institute of Biochemistry, the Bringing Materials to Life Consortium, and also the Cogito Foundation, who has sponsored very generously these activities. And at the end, I would like to ask you, if you have a little bit of time, to fill out a survey to tell us what you think, what you've enjoyed, and also what we can make better. Because, as I said, we are learning in this process, so we would like to get your feedback, your opinions on how we can grow this further. And otherwise, thank you very much for coming. Thank you, Shem, and I wish you a nice evening.